Welcome all. Myself Dr. Vivek MS, Assistant Professor in Department of Chemical Engineering. Today we are going to see two major topics in chemical reaction engineering. So first we are going to see the design of continuous reactors. Also we are going to see stirred tank reactor and tubular reactors. So the design of continuous reactors are both for continuous stirred tank reactor, that is CSTR, and plug flow reactor. So this is in other name is also called as stirred tank reactor, which is CSTR, and the other name of plug flow reactor is tubular flow reactor. So moving on to the topic, the modes of operation are basically of three types. So majorly they are batch reactor, steady state flow or continuous flow reactors, that is we can tell as PFR or MFR. The third one is unsteady state flow or semi batch reactors. So there is a diagrammatic representation here where a batch reactor is here with a composition of reactant inside with a pressure gauge attached to it, and there is an output and input in the reactor with a average stirring speed given in it. So we can see continuous flow reactors. This is another name we can tell as MFR, or we can tell it as a plug flow reactor. So in continuous flow reactor, it will be in a tube shaped reactors, so where feed is given from one side and product is achieved from the other side. So the composition at any point is unchanged with the time in a continuous flow reactors. Whereas in semi batch reactor, you can see the reactant A is present in the reactor and reactant B is added with different volume. So after some time, after a reaction occurs, there will be a change in the composition of the reactant, and further we will be moving to the third part where the product has been achieved. So this is the material balance for any reaction. First reactor enters to the reactor and reactant leaves. So that can be taken as the time where the reactor enters and reactor leaves is space time, or it can be in other word we can tell as residence time. So the reactor is present at a particular volume which is denoted as elemental of reactor volume. Also when there is a material balance of an element of volume of reactor, we can check that the reactant disappears by reaction within the element. Also there is a reactant accumulation within the element. So we can write the material balance as rate of reactant flow into element of volume is equal to rate of reactant flow out of the element plus rate of reactant loss due to chemical reaction within the element of volume plus rate of accumulation of reactant in the element of the volume. So in general we can tell as input is equal to output plus accumulation plus disappearance. So this is what we are writing in the material balance. Next we will go on to the energy balance for any reactant in the reactor. So here heat enters the reactor and heat leaves the reactant with the same reaction time taking place. So here we can write the energy balance as rate of heat flow into the element of volume is equal to rate of flow out of the element of the volume plus rate of disappearance of heat by reaction within the element of the volume plus rate of accumulation of heat with the element of volume. So this is how energy balance has been written. So both material balance and energy balance has to be derived to find the conversion percentage or the yield percentage of the product in a reactor. So basically design of continuous reactors are of two types. One is mixed flow reactor, the other is plug flow reactor. So the mixed flow reactors are always homogeneous liquid phase reactions. Also plug flow reactors are also homogeneous gas phase reactions, whereas you can see in a mixed flow reactor there is a impeller attached to the reactor and there is a continuous feed given and there is a uniform mixing by the impeller and the product has been achieved. Similarly, you can see here in the plug flow reactor a feed is given in a tubular shaped reactors and there is a flow, straight laminar flow, and the product has been achieved from the other side. So this is the difference between the mixed flow reactor and the flow reactor. So design of continuous reactors. So let us assume both the reactors, mixed flow and plug flow reactors, are at steady state flow. So when a fluid passes through the reactor with no mixing of earlier and later entering fluid or with no overtaking, it is fluid moved in single file through the reactor. In a CSTR, whereas or a mixed flow reactor, uniformly mixed same composition everywhere with the reactor at the so some of the advantage and disadvantage of MFR or CSTR we can take as first the advantage we see easy to maintain good temperature control with the reactor, possible to operate the reactor under isothermal conditions even when the heat of reaction is high, low cost construction, provides long residential time due to its large volume. CSTR runs at optimal temperature for long reaction times. Whereas disadvantages, we can see the conversion of reactant per unit volume of reactor is small, not recommended for high pressure operations because of cost consideration, not suitable for reactions with very high heat effects due to availability of low area of heat volume per volume, low heat transfer coefficient. Similarly, moving on to the plug flow reactor, on the advantage and disadvantage, we can check that there is a easy maintenance of advantage, highly conversion per unit volume of reactor, suitable for high pressure reactants because of cost consideration, high heat transfer coefficient. Whereas disadvantage, if we see, we can see there is a difficult to control temperature within the reactor, hot spots can occur within the exothermic reaction, and this is the main disadvantage advantage we have seen both for MFR and PFR. So moving on to the space time. What is space time? It is nothing but it is the time necessary to possess one reactor volume of feed at a specific conditions. So in other words, we can tell as it's a residence time. The amount of time that is required for the reactant to completely react inside the reactor and forms a product. So the time of the reactant spent inside the reactor is measured as space time or residence time in time units. So it can be given as tau by V by V naught. Also space velocity. Here moving on to space velocity, we can tell it as it is the number of reactor volumes of feed at specified conditions which can be treated in unit time. So the space velocity, it is denoted as S and it is given as 1 by tau, that is 1 by space time or residence time, that is V naught by V, that is given as Fa naught by Ca naught by V, that is feed of the reactant divided by concentration of the reactant divided by the volume of the reactor, and finally it will be equal to the feed of the reactant divided by concentration of the reactant, that is Ca naught, into volume of the reactor. So this is what we have seen in today's topic. So thank you very much. We can meet with a different topic in the next video.